Welcome everyone. I'm Wille, Associate Professor at the University of Connecticut, and it is my pleasure to share some information of our research with you. Development and testing of ultra-high early strength concrete for durable bridge components and connections, which is part of the Thrust 2 New Materials for Longevity and Constructability. A few words to our motivation and objectives. Increased traffic loads have given rise to the need of bridge structures with increased load resistance. Increased traffic and the economical impact of disrupting the traffic flow have given rise to bridge structures with enhanced durability and reduced maintenance and quicker construction by utilizing the concept of accelerated bridge construction. The aging of our infrastructure is at a critical point where, for example, 42% of the bridges are at least 50 years old and 70.5% of the nation's bridges are considered structurally deficient as per ASCE Report Card 2021. And thus, there is a general need for bridge structures with enhanced sustainability and lifespan. One of the objectives of this research is the development of cost-efficient, non-proprietary high and ultra-high performance concrete mixes for the use in bridge construction to address this need. The materials could be either used for cast connections, as you see in the figure here, or for casting the bridge girders and decks. Highlighted in red is what I will be focusing on today. You see that one main task of the entire research project is developing non-proprietary UHPC using local available materials within the New England area. Another major task is the knowledge transfer and practical application, highlighted in purple here, which will be the focus of this project in the future. Why UHPC? Most of you probably have already heard of UHPC. It is a cementitious composite with a relatively high amount of binder in comparison to conventional concrete. It's designed to use a water-to-binder ratio of less than 0.2, achieves compressive strength in excess of 150 megapascal or 22 ksi, and the addition of tailored discontinuous fiber reinforcement leads to significantly higher ductility and durability of the cracked composite. The key for the strength and durability properties is a very high packing density of the matrix. The properties of UHPC are exciting, and its application in bridge construction has a great potential to address the current and future needs of our infrastructure. Our research steps included identifying suitable material suppliers in the New England area, then selecting suitable materials for the matrix, applying UHPC principles in the mix design and mixing process with the goal to enhance matrix density, perform an experimental investigation and material characterization, then tailoring the concrete matrix based on an efficiency factor E, taking into account compressive strength, workability, and cost. This will lead to an optimized UHPC matrix or matrices. As a next step, suitable fibers are being selected as discontinuous reinforcement. Emphasis is placed on fiber efficiency, workability, and performance of the composite. This is very critical for the development of cost-efficient UHPC since fibers are the main cost factor of UHPC. Next, I like to share various test methods we have used and enhanced for this research. For example, mixing. In the first phase of paste development, we used a resonance frequency mixer due to its high mixing consistency, short mixing time, and quality of particle dispersion, without the use of any mechanical mixing tools. To the top right, you see an acceleration versus time diagram, complemented by pictures showing the change from wet particle clumps to an homogeneous UHPC paste mixture. Due to the limited mixing volume, a mini flow cone was designed and used for measuring the spread. When mixing UHPC, we usually used the tabletop mixer displayed here and followed a strict mixing protocol for enhanced consistency, as listed here. The workability was measured by the spread using a regular flow cone. Compressive strength has been tested using 2x2 inch cubes. Prior to testing, the load phases were ground until passing the quality control. Rotating ball-bearing loading platen were used for testing the cubes in compression at a loading rate of 30,000 pounds per minute. Tests typically run from 2.5 to 4 minutes. Without fiber reinforcement, the cubes failed explosively. The addition of sufficient steer fibers changed the failure from being brittle to ductile, as you can see in the pictures to the right. For direct tensile testing, dog bone-shaped specimens were used with embedded mesh reinforcement at the ends. Here, the embedded end reinforcement has been placed on the failed specimen to illustrate the location of the mesh. The test setup had been significantly improved to provide rotational freedom to the specimens, see pointed arrows, as well as reliable deformation measurement. As a result, the displayed test results here show high consistency and quality, which is usually challenging to obtain. In preparation for the investigation of fiber reinforcement efficiency, an improved single fiber pull-out test setup has been developed. You see here highlighted in red the illustration of the embedded fiber. A load cell measures the pull-out load while the LVDT measures the fiber slip. This test setup has successfully been tested, and more tests will follow to characterize the bond between fiber and UHPC matrix. In terms of durability properties, we have started to test the UHPC surface resistivity, which is indicative of the pore structure and the permeability of the matrix. We also have started to test UHPC beams in the freeze-thaw table. Another parameter to pay attention to is the amount of entrapped air. We have used two approaches. First, the mini air meter for total air void content, and second, filling air voids of the ground UHPC surface, followed by digital photo analysis. Then the air voids have been linked to the compressive strength, and a linear correlation between them has been drawn for the mixes investigated in this part of the research. This is important for a representative comparison of the compressive strength of mixes with different air content. Research progress and outcomes. Besides our progress in enhancing our test setups, we have significantly progressed in material testing. So far, more than 60 paste mixes have been performed, usually small volumes of 0.16 liter, mostly mixed with the resonance frequency mixer, with a water-to-cement ratio of 0.23 to 0.25. So first, we started with our house UHPC mix as a reference mix, using white cement, white silica fume, silica powder, silica sand, and high-range water reducer. Then we replaced several material constituents once at a time, for example, changing the type of cement, type of supplemental material, which included fly ash, glass powder, and slag, and switched to basalt aggregates, locally available here in Connecticut. We analyzed the results as a next step, and based on the E factor, which takes into account strength, workability, and cost, an optimized paste has been finalized. Using the optimized paste, we move to the next step, UHPC. So far, we have mixed about 50 UHPC mixes at a volume of 2.1 liter each. The water-to-cement ratio is usually in the range between 0.23 and 0.25, and the aggregate to the cement ratio were investigated from 1.2 to 1.8. Aggregate particle distribution was tailored to follow the modified Anderson and Andreasen curve. In terms of fiber reinforcement, we started to add fibers in the volume fraction of 1, 1.5, and 2% and use different types of fibers available in the US. Here I'd like to show some more results. For example, you can see the effect of cement replacement by slag. You see all mixtures exceeded a compressive strength of 150 megapascal while having a sufficient workability. Increase in cement replacement by slag slightly increased the strength and led to a decrease in workability starting at 40% of replacement, as you can see with the orange curve here. In terms of silica fume to cement ratio, the diagram at the bottom right here, you see best workability and strength at a ratio of 20%. Here you see the effect of adding more aggregates and fibers on the workability of the mix. As you can see, the spread decreases with the increase in aggregate to cement ratio. So the more aggregate you add, the more you lose workability. A similar trend is seen with the addition of fibers. The more fibers you add, here 0, 1 and 2 volume percent, the more you lose workability. The diagram is also an excellent indicator how changing the aggregate to cement ratio can be used to offset the effect of added fiber reinforcement. For example, if you like to achieve a spread of 270 mm, measured with the flow cone here, then an aggregate to cement ratio of 1.7 can be used without fibers. But if you want to add 2 volume percent of fibers, then the aggregate to the cement ratio should be limited to 1.3 and thus still achieving the same spread. Preliminary results obtained by the direct tensile tests and the single fiber pull-out tests are shown here. Both results are very promising. The direct tensile tests show great consistency, strain hardening behavior, a tensile strength of up to 2 ksi, and ductile behavior indicated by a peak strain of more than 0.5%. The pull-out results show high load resistance and shear strength hardening. This is seen by keeping the pull-out load almost constant, although the fiber is being pulled out and thus steadily reducing its embedded length. More tests will come. Last but not least, you see here preliminary results of the electrical surface resistivity of over the age of the UHPC. The threshold of the definition of low permeability concrete has been plotted here in red. So after 4 days, UHPC surpasses already the threshold of 27 kiloohm centimeters and continues increasing the resistivity until reaching a measurement of 1000, which reaches the detection limitation of the equipment. This means that the pore structure indeed extremely densifies with aging of the concrete, and this is a key property for long-lasting durability of the material. So this is good. So the following conclusions can be drawn. We were able to further enhance and improve specimen preparation and testing methods for enhanced test results consistency. We successfully developed UHPC mixture designs using locally available materials and obtained promising workability results, mechanical and durability properties. In the future, we plan on further investigating the durability properties, studying the fiber efficiency, and perform cost analysis, and transfer the knowledge to UHPC technology to local precast companies. I want to express my gratitude to the following centers, departments, schools, and companies for their support here. This includes TIDC, Condat, IMS at UConn, Lafarge-Holcim, Steel Like Concrete, Fibercon, Beckert, Hyperfiber, Lehigh Cement and Lehigh White Cement, Norcam, Borough, Dilcon, the ACMC Lab, and the School of Engineering at UConn. And thanks to all graduate and undergraduate students who supported this research, despite the challenges due to COVID-19 last year. Thank you.